Hello everyone, welcome to module 6. In this module we're going to discuss acids and acid-base equilibria. So in this lecture we're going to discuss acids and bases in water, autoionization of water and pH scale, proton transfer and the Bronsted-Lowry definition of acids and bases, and solving problems involving weak acid equilibrium, weak bases and their relation to weak acids, molecular properties of acid and acid strength, acid-base properties of salt solutions, generalizing the Bronsted-Lowry concept, and finally electron pair donation and the Lewis acid-base definition. So let's start with some of the common acids and bases and their household uses. So let's take first acetic acid, which is one of the most commonly used acids, mostly used as flavoring and a preservative in the form of vinegar. You have citric acid, which is generally used as a flavoring, most commonly also found naturally in citrusy fruits, things like orange, lemon. And you have ascorbic acid, also called vitamin C, and it's also used as a nutritional supplement. And you have aluminum salts, where they are generally used in baking powder with sodium hydrogen carbonate. Let's look at some of the bases. Start with sodium hydroxide, more commonly used as oven and drain cleaners. Ammonia, used as a household cleaner. Sodium carbonate, used as a water softener and grease remover. And you have sodium hydrogen carbonate, which is generally used as a fire extinguisher, rising agent in cake mixes, generally called as baking soda, and as a mild antacid. You have sodium phosphate, used as a cleaner for surfaces before painting or wallpaper. So let's start with the Arrhenius acid-base definition. So Arrhenius definition is the earliest acid-base definition, which generally classifies these in terms of their behavior in water. So we base the Arrhenius definition on the idea that how does the acid or a base behave in water. So what is an acid? So an acid is a substance that with a hydrogen in its formula that dissociates to yield H3O+. So H3O+, also called as the hydronium ion. And you have a base is a substance with OH in its formula that dissociates to yield OH-, more commonly known as the hydroxyl ion. So one is the hydronium ion. So if it releases a hydronium ion, it's an acid. If it dissociates and forms a hydroxyl ion, it's a base. Now when an acid reacts with a base, they undergo what we call as a neutralization reaction, where the hydronium ion and the hydroxyl ion combine to form water back again, and it's still an exothermic reaction which results in a release of energy. So let's start discussion about strong and weak acids. So how do we classify acids? So an acid that dissociates completely into ions, which means that all of the acid molecules are converted into the A- molecule. So where HA gets converted into A- and all the hydrogens in HA form hydronium ion, we call that a strong acid. So what happens here is a displacement reaction where the hydrogen goes to H2O+, combines with it and forms H3O+. And you have a dilute solution of a strong acid generally contains no HA molecules. So this is the idea behind a strong acid. Next, let's take a weak acid. So weak acid is something that dissociates slightly to form ions, which means not all of the molecules are completely dissociated. Only a small percentage of the molecules are dissociated to form H3O+ and A-. The rest of it stays as it is, undissociated. This type of an acid is called as a weak acid. So which means the equilibrium constant here generally has a really small value for weak acids. So let's take an example of a strong acid dissociation here. So before the concentration of HA is, let's say, right here, this amount. After dissociation, there is no HA present. All of it is converted into H3O+ and A-, so which means that if you check in the liquid, there is no HA molecules left. So this is an example of a strong acid. In a weak acid, most of the HA molecules are undissociated. Only a small amount of molecules are converted into H3O+ and A-. The rest of them stay intact. So all the molecules that you see here are HA molecules, and you only see some amount of molecules that are converted into H3O+ molecules. Next, so let's look at an example of a reaction of zinc with a strong acid and a weak acid. So when you dissolve zinc into a strong acid, it dissociates rapidly to form the zinc dissociator reacts with the strong acid very rapidly because there is a high concentration of hydronium ions. So next, let's take a look at another type of constant called the acid dissociation constant, Ka. So let's take a simple simple definition of an acid. You have Ha reacting with H2O to form H3O plus A minus. Now when we write the equilibrium constant, we can write it as the concentration of H3O plus times the concentration of A minus over the concentration of Ha times the concentration of H2O. Now the ones that are undergoing change are Ha, H3O plus and A minus, but the only liquid that is present here is Ha, which is not going to change. So when you bring Kc times H2O, that becomes H3O plus times A minus over Ha. So this constant, where equilibrium constant, the product of the equilibrium constant and the water concentration, is called as the acid dissociation constant. So which is written as H3O plus times A minus over H. So this here is the acid dissociation constant. So what does the acid dissociation constant has to say? So let's take an example. If you have a really strong acid, so in a strong acid, we know that the H3O plus concentration is really high, which means Ka is also high. When you have a weak acid, H3O plus concentration is low, which means Ka concentration is also low. So Ka is a good measure of the strength of an acid. So this is the one that is generally used to check the strength of an acid. So as you notice that the stronger the acid, the higher the Ka value. The weaker the acid, the smaller the Ka value. Now, classifying acids based on the relative strength, let's take an example of strong acids. So how do you classify a strong acid? They generally include the hydrohalic groups. Hydrohalic groups are HCl, HBr and Hi, and also oxo acids in which the number of oxygen atoms exceeds the number of ionizable protons by 2 or more. So which means, for example, let's take a difference between HNO2 and HNO3. So if the number of oxygen atoms that are present exceeds the number of protons by 2 or more, we call that a strong acid. So here it exceeds the ionizable protons by 2, so we can say that this is a strong acid. While notice here it exceeds the ionizable protons by only 1, so we can say that this is a weak acid. So this is how we classify oxo acids based on their relative strength. So next, let's take a look at weak acids. So weak acids generally include hydrofluoric acid and acids in which the hydrogen is not bonded to the oxygen or to a halogen. For example, HCl, which is cyanic acid, hydrocyanic acid, and you have oxo acids in which the number of oxygen atoms equals or exceeds the number of ionizable protons. So more common examples of these acids are HClO and HNO2. So these are examples of oxo acids that are weak, and all carboxylic acids, which are basically general acids with the group COOH. So any acid with the group COOH is generally called as a carboxylic acid. So these groups are generally more commonly very weak acids. So an example of that is acetic acid, and you have hexanoic acid. Next you have bases. How do you classify the relative strength of the bases? So what are the strong bases? They include water-soluble compounds containing O2 minus or OH minus ions. Second, the cations are generally the ones usually the most active metals. So an example of that can be in the form of M2O or MOH, where M can be a group 1 element like lithium, sodium, potassium, rubidium and cesium, or MO or MOH2, where M can be group 2 elements such as calcium, strontium and barium. So these are strong bases. Next you have weak bases. They include ammonia and derivatives of ammonia called amines. Amines are basically where one hydrogen is removed from ammonia and replaced with another group, but doesn't change the actual nature of the molecule, so which means that they stay as a weak base. And the common structural feature in a nitrogen atom with a lone electron pair are generally the ones with weak bases. So let's take an example and classify each of these as a strong acid, weak acid, strong base or a weak base. So let's take a look at first one, KOH. So K and OH. So we know that when OH is present and the metal is an active metal, this is a strong base. Why is this a strong base? Remember that K is a group 1 element and OH minus ion is the one that's going to release it, so which is also a strong ion, so it becomes a strong base. Second, notice that you have COOH here, so which means that this is a weak acid. Next, you have H2SeO4. Notice here in C, this is an oxo acid with oxygen, and there are 2 ionizable protons, and it exceeds the number of ionizable protons by 2, so which means that this is a strong acid. Next you have NH2. Notice NH2 here, so this is in the form RNH2, so which is a weak base. So this is how you can classify acids as strong or weak. Next, let's talk about autoionization of water. So water molecules in general undergo a process called self-ionization or autoionization, where one molecule starts to act as an acid and the other molecule starts to act as a base, resulting in a neutralization reaction which releases the form H3O plus OH minus. So this is really slight and it's really small, that it's nearly insignificant in terms of the actual quantity. But understanding autoionization gives a view into how water molecule generally behaves. So let's take a look at a general water molecule. So you have oxygen with 2 hydrogens and 2 pairs of lone pairs of electrons, and you have, let's say, another water molecule here with another 2 lone pairs of electrons. So one of the oxygens donates its lone pair to the another oxygen molecule. It results in the structural formation where oxygen has hydrogen, resulting in 2 electrons only, and you have oxygen with 3 hydrogens So the oxygen with 3 hydrogens and 1 oxygen with 3 electron pairs. So when the lone pair goes in, the oxygen generally results in the donation of a hydrogen group here. So which means that this hydrogen is going to disappear. So you have 1 oxygen, so one where we have oxygen, so you have H3O plus, which is this molecule, and another side you have OH minus, which has an excess pair of electrons resulting in a negative charge, and H3O plus has a deficiency of 2 electrons resulting in a positive charge. So this process is called as self-ionization, where it creates its own ions by combining with each other, or also called autoionization. So why do we need to know this? So let's take a look at another common constant called as the ion product constant. Let's take a look at the autoionization process, and let's write the equilibrium constant for the autoionization process. So this results in H3O plus times OH minus over H2O square. Now when you write it as Kc times H2O square, you get, on the other side, you get H3O plus times OH minus. So this value is a constant, and that value is generally 1.0 times 10 to the power negative 14. and this value here is called as Kw. It's also called as the ion product constant of water. So ion product constant of water. So this value is called Kw. So from this we can write that Kw equals H3O plus times OH minus, which is equal to 1.0 times 10 to the power negative 14. So this here is the ion product constant of water. Now what happens if we change one of the concentrations? Let's say, for example, you have water and you have added an acid. So when you add acid to water, what happens now? There is an increase in the H3O plus concentration. So when there is an increase in the H3O plus concentration, remember that if this increases, to maintain the constant value, the other one has to decrease. So which means that the OH minus concentration goes down, to make sure that the product value stays constant. Now when you add a base, the base results in the increase of OH minus values, which means that increases the OH minus concentration. Now if there is an increase in the OH minus concentration, which means that there should be a decrease in the H3O plus concentration. So using this principle is how we know whether a solution is acidic or basic. So in an acidic solution, H3O plus concentration is greater than the OH minus concentration. In a basic solution, H3O plus concentration must be less than the OH minus concentration. But in a neutral solution, so a neutral solution is generally the one that is generally constant, which means that to maintain that it should be water, it should be equal. So H3O plus concentration should be equal to the OH minus concentration. So that is the idea behind an acidic, neutral and basic solutions. So when H3O plus increases, which means that OH minus has to decrease to maintain the Kw value, which results in an acidic solution. When there is no acid or a base, which means that both concentration must be equal to make sure that the concentration is neutral, the solution is neutral. Now if you add a base, then the OH minus concentration will increase and resulting in the decrease in H3O plus concentration, resulting in the formation of a basic solution. So let's take an example. So what is given here? A research chemist adds a measured amount of HCl gas to pure water at 25 degrees centigrade and obtains a solution of H3O plus with a concentration of 3.0 10 times 10 to the negative 4. Calculate OH minus and is the solution neutral, acidic or basic? So what is given here is they have given us the H3O plus concentration, which is 3.0 times 10 to the power negative 4 m. And we do not know the OH minus concentration, but we do know the product of these values Kw is going to be 1.0 times 10 to the power negative 4. So we know that Kw, the formula of that is H3O plus times OH minus. So to find the OH minus concentration, we can write it as Kw over H3O plus. So which can be written as 1.0 times 10 to the power negative 14 over 3.0 times 10 to the negative 4. So 1 by 3 times 10 to the power negative 14 plus 4. So which is going to be 0.33 times 10 to the power negative 10. So which can be written as 3.33 times 10 to the power negative 11 m. So this is the OH minus concentration. Notice that there is an increase in the H3O plus concentration is high, so which means that OH minus concentration is low. So when you compare H3O plus and OH minus, notice here that H3O plus is greater than the OH minus concentration. So this condition is generally when you have an acidic solution. So this here is an acidic solution. And this is how you can solve the problem to find the OH minus concentration for the liquid that is given here. Next, let's talk about the pH scale. So pH is basically standardizing the concentration values to a simpler value. So pH is the negative logarithm to the base 10 of the H3O plus concentration. So whenever you see the term P and you borrow it by any value A, so it's always going to be negative log to the base 10 of the concentration of that particular material. So this is the idea behind the pH values. So pH values are generally simply written as negative log of H3O plus, understanding the idea that log refers to log base 10. Remember that when you write ln, it refers to log base E, but we do not use log ln here, we use log here. So this is the pH scale. Now, what happens to the pH values in terms of the acid here? Now, if the pH value is greater than 7.00, let's start with, if the pH value is less than 7, that is an acidic solution. If the pH value is equal to 7, then that is a neutral solution. If the pH value is greater than 7, that's a basic solution. So the pH value determines whether the solution is an acid or a neutral solution or a base. So the higher the pH value, the lower the H3O plus concentration and the less acidic the solution. So as the pH value increases, the H3O plus concentration decreases. So this is the idea behind pH values. And let's look at some of the common household items that we generally see with the various pH values. So 1M hydrochloric acid contains a pH value of 0, so which is really strong. Stomach acid ranges with around 1 to 3 based on whether the stomach contains food or does not contain food. Lemon juice has about 2.2 to 2.4, vinegar from 2.4 to 3.4, beer from 4 to 4.5, unpolluted rainwater from 5.6, urine ranges from 4.8 to 7.5, milk around 6.4, and pH value of 7 is neutral, more commonly the general distilled water, and you have blood at 7.4, seawater from 7 to 8.3, detergent solution from up to 10, milk of magnesia up to 10.5, household ammonia 11.9, lye 13, and 1M NaOH is about 14. So these are the household items and their pH values based on the values that you see here. So what is the relationship between Ka and pKa then? So just like pH, pKa is the negative logarithm to the base 10 of the Ka value. So pKa is generally used for weak acids. So it's generally used to compare between weak acids. So let's say, for example, you can put a broad class of acids into weak acids, but to know which of the weak acids is the most stronger of all the weak acids, that generally is used under pKa values. So a lower pKa value corresponds to a high Ka value. So the lower the pKa value, the higher the lower the Ka value, the higher the pKa value. So that is the idea behind Ka and pKa. Now let's take a look at pH, pOH and pKw. So I already told you that whenever you use the term P, it means that when you use pH, it's the negative log of H3O plus, and when you use pOH, it's the negative log of OH minus. And the term pKw here refers to the idea that we can write the negative log for Kw as well. So this pKw value is the basis on which we generally do all of these calculations. So we know the Kw value is about, so negative log of 1.0 times 10 to the power negative 14. So when you remove 1.0, so you get log to the power 10 to the power negative 14. So when negative 14, we know that, log, when you put the power comes to the front. So negative of negative 14 times log 10 base 10, so which can be 1. And minus minus get cancelled. So we know that pKw here equals 14. So what is the relationship between pKw and pH and pOH? So always remember that pH and the sum of pH and pOH of any solution must always be equal to 14, which is basically equal to the value of pKw. So this is the formula based on which, so for example, if you have a solution with a pH of 4, so its pOH can be written as 14 minus pH, so which can be written as 14 minus 4, so which is 10. So a solution with a pH of 4 can have a pOH of 10. So this is the idea behind pH and pOH values. So again, to summarize this, the lower the H3O plus concentration, the higher the pH value. The higher the pH concentration, the H3O plus concentration, the lower the pH value. So this is the idea behind H3O plus, the concentrations. So next, what is given here? Calculate H3O plus, pH, OH minus and pOH for each solution at 25 degrees centigrade. So they have given 0.30 m HNO3 used for etching copper metal and 0.0042 m COH2 used in leather tanning to remove hair from dyes. So let's take an example here of HNO3. Now notice that HNO3 is a strong acid because it has more oxygens in compared to the ionizable number of protons. So which means that, so when you look at the dissociation reaction of HNO3 with water, you notice that it's going to become H3O plus plus NO3 minus. So which means here, for each 1 mole, notice that it's a strong acid, which means it dissociates completely. So which means that this is going to be having the same concentration. If this is 1 mole, this is also going to be 1 mole. But in the value that is given that it's 0.30 mole, so which means that if this is 0.30 mole, this is also going to be 0.30 mole. So which means that the H3O plus concentration here is going to be the same as that of the acid concentration. So we have found H3O plus. Next we have to find pH. So pH is the negative log of H3O plus. So which is the negative log of 0.3. So use a calculator and this value becomes pH equals 0.52. Now we have found pH. So based on the pH value, we know the formula that pH plus pOH equals 14. So which means that we can find pOH, which is equal to 14 minus pH. So which is going to be 14 minus 0.52, which is going to be 13.48. So this is the pOH concentration. So we found the pH and pOH. Next we need to find OH minus concentration. We know that Kw, which is equal to H3O plus times OH minus equals 1.0 times 10 to the power negative 14. So we have the H3O plus concentration already given, 0.3 times OH minus equals 1.0 times 10 to the negative 14. So OH minus concentration can be written as 1.0 times 10 to the power negative 14 over 0.3. So which gives you a value of 3.3 times 10 to the power negative 14 m. So this is the concentration of the OH minus ion. So we have found everything. We have found pH, H3O plus, pOH and OH minus. So next they have given, in the next part of the problem, they have given us COH2, which is 0.0042 m COH2. Now let's take the value taken here. So if you take COH2 and try to dissociate it, so CaOH taken twice plus H2O, or we can write directly CaOH taken twice, when you mix it directly, it results in Ca2 plus plus 2OH minus. So for every 1 mole of CaOH2, there is 1 mole of Ca and there is 2 moles of OH minus. So which means that they have given an initial concentration of 0.0042. So which means this is going to be 2 times that of the original value. So which is going to be 0.0084 mole. So the initial concentration of OH minus, so the OH minus concentration is going to be 0.0084 mole. Now based on OH minus concentration, we can directly write the formula for POH, which is going to be log of OH minus, negative log of OH minus, so which is going to be negative log of 0.0084. So that gives you a value of 2.08, which is going to be the POH concentration. Now we need to find the pH. So we know that pH plus POH is 14. So pH can be written as 14 minus POH, which is going to be 14 minus 2.08, which is going to be 11.9. So this is the concentration of pH. Now we know that the concentration of H3O plus times OH minus is 1 times 10 to the power negative 14. And from this we can write H3O plus concentration as 1.0 times 10 to the power negative 14 over OH minus concentration. So which is going to be 1.0 times 10 to the power negative 14 divided by 0.0084. So which gives you a value of 1.2 times 10 to the power negative 12 m. So which is the concentration of H3O plus. So let's move on to the next topic, the methods of measuring the pH value of an aqueous solution. So we know the two methods that are generally used are a pH paper, which generally gives you an approximation of the pH of the acid. So generally a pH paper contains a strip of a paper, more commonly an orange coral paper, and when you drip it in a solution, if the solution is acidic, it turns more redder towards the red, and if it's more basic, it turns blue. That's generally a pH paper. The another one that gives you a precise measurement is a pH meter, which generally uses electrical current to measure the electrical potential to measure the pH of the solution. So next, let's get into the next type of definition called as the Bronsted-Lowry definition of acids and bases. So Bronsted-Lowry definition gives the idea based on the protons. So the material that accepts the proton is called as the base, and the one that donates is the acid. So an acid is a proton donor, and any species that donates a H plus ion is considered an acid. Most commonly it should contain a hydrogen in its formula, and a base is a proton donor, and any species that accepts the H plus ion, generally H plus contains a lone pair of electrons to bond with the hydrogen. And an acid-base reaction is basically a proton transfer process where the proton is getting transferred from the acid to the base. So let's take a simple example of an acid-base reaction and let's take a look at it. So let's say we have HCl reacting with H2O. So HCl, when it reacts with H2O, it forms H3O plus Cl minus. So what happens here? You have hydrogen bonded with chlorine. So with chlorine having 4 lone pairs of electrons, 3 pairs of lone electrons, and you have oxygen, which has 2 lone pairs of electrons and 2 hydrogens. So when they combine, what happens here is HCl is the proton donor, so where it donates a proton to the oxygen. And what happens here is that you have oxygen. So the hydrogen does not take its electrons, so it rather bonds with the electron pair of the oxygen, resulting in the formation of H3O plus ion, the hydronium ion, with 1 lone pair of electrons. So this here, so the lone pair that you see here is this bond. So and the Cl keeps its electrons to itself, resulting in the formation of Cl minus ion. So this here is the idea behind the Bronsted-Lowry definition of an acid and a base. So let's take a look at example here. So which is the one that donates here? So this is the proton donor, So this is the proton acceptor. So this becomes the acid and this becomes the base. So this is the idea behind an acid-base reaction. Now something interesting comes through here. So let's take a simple example of this same reaction right here. Now notice that this is the proton donor. Let's take a look at the reaction in reverse. So in reverse you have Cl minus plus hydronium ion forming HCl plus H2. So in the reverse reaction, notice that the hydronium ion is the one that donates the proton to chlorine, and the one that accepts here is the chlorine. So here this becomes the acid, this becomes the base, and this becomes the acid. So which means that this here is acting as the acid and this here is acting as the base. So how do you understand this in reverse reaction? These are what we call conjugate acid-base pairs. So this here is called as the conjugate acid. So an acid, when it donates its proton, becomes a base. So that base is called as the conjugate base. And a base, when it accepts the proton, it becomes an acid, also called as the conjugate acid. So in the forward reaction, one becomes the acid. In the reverse reaction, the same compound becomes the base. So these are what we call conjugate acid-base pairs. So these are called as the conjugate acid-base pairs. So here H2S and HS minus are a conjugate acid-base pair. And HS minus here becomes the conjugate base of H2S. Notice that here this is the acid and this is the base. So which means that the acid creates a conjugate base and a base creates a conjugate acid. So NH3 and NH4 again conjugate acid-base pair. NH4 plus is the conjugate acid of the base NH3. So Bronsted-Lowry acid-base definition occurs when an acid and a base react to form their conjugate acid and a conjugate base respectively. So this is the idea behind the Bronsted-Lowry definition of a conjugate acid-base pair. So the acid creates a base and a base creates the acid. So this is the idea behind here. So here HF is the acid, the conjugate base is F minus, H2O is the base, H3O plus is the conjugate acid. Again, HCOOH is the acid, HCOO minus is the conjugate base, CN minus is the base, HCN is the conjugate acid. So this is how we generally determine the conjugate pair of acids and bases. So let's take an example here. So the following reactions are important environmental processes. Identify the conjugate acid-base pair. So let me write the acids in black and the base in red. So let's take a look at the reaction right here. Notice that H2PO4 becomes HPO4 minus, which means it loses a proton. So this here is the acid. So this here is the acid and this is the conjugate base. CO3 minus is the base, HCO3 minus is the conjugate acid. Again, let's take at the next reaction. Let's look at H2O here. H2O, it becomes OH minus, which means it loses a proton, so it's a proton donor. So which means that this here is the acid, OH2 minus is the conjugate base. So let me write it down right here. So this is the acid and this is the conjugate base of the acid. This is the base and this is the conjugate acid. Again, this is the acid, this here is the conjugate base and this is the base and this becomes the conjugate acid. So this is how we can write acid-base pairs. So let's look at the net direction of reaction. So understanding the conjugate base and gives you only a certain level of understanding of this, but the next one to understand is what direction in which the acid-base reaction generally goes. So the net direction of an acid-base reaction generally depends on the relative strength of the acids and bases that are involved. The main point to remember is that the reaction will always favor the formation of a weaker acid and a weaker base. So which means that, let's say for example, when you have H2S mixing with NH3 forming HS minus and NH4 plus, notice that HS minus is a weaker base and NH4 plus is a weaker acid, which means that the reaction will favor the side that is weaker in comparison, and which means that when the weaker side is the product, so which means the reaction favors the formation of the products. So again, let's take a look at right here. So how do you understand this? A stronger acid always yields a weaker base. Remember this, that the stronger one always, the conjugate of a stronger one is always a weaker one. So the conjugate of a weaker one is a stronger one again. So strong base leads to a weak acid, strong acid leads to a weak base. So a strong acid results in a negligible strength base. A weak acid results in, so a negligible strength acid results in a strong base, and a weak acid results in, so the comparison is that as you go towards higher acid strengths, their conjugate bases have decreasing base strength. So let's predict the net direction and whether Kc is greater than 1 for each of the following reactions. So let's take the first reaction. So the first reaction, you have H2PO4 minus plus NH3 results in HPO4 2 minus plus NH4 2 plus. Now we have to identify the conjugate acid-base pairs based on the table right here. We have H2PO4 plus, or 2PO4 minus, and HPO4 2 minus, NH3 and NH4 plus. First, let's determine the acid-base pairs. So notice that H2PO4 minus, H2PO4 minus and HPO4 2 minus, there is a proton loss, which means that this acts as a base. So this is acid 1. This becomes the base 2, which is the conjugate base. So here, this is the base 1. And this is the acid 2. Now here to compare, we have to compare the acid 1 with acid 2 from the table. So we are comparing two acids, H2PO4 minus and NH4 plus. So H2PO4 minus and NH4 plus. So notice that this is in the increasing acid strength, which means that H2PO4 is stronger than NH4 plus, which means that this is stronger and this is weaker. Now let's go to the base side. You're comparing NH3 with HPO4 2 minus. So you have NH3 with HPO4 2 minus. Notice that we are talking about in the reverse direction here. So which means NH3 is stronger than HPO4 2 minus. So this is NH3 is stronger and this is weaker. Now we have compared these. Now which side is the weaker side? So we notice that this side is the weaker side. So which means that the reaction will favor the direction which is weaker. So which means that the reaction will favor the right side. So which means the net reaction favors the formation of products. So the net reaction here favors the formation of products. Always remember, first write down the acid-base pairs and then compare the acids and compare the bases based on that table. So that will give you an idea behind the reaction. Now, because the reaction is favoring the products and you have stronger acid-base pairs, so how do you write the Kc value right here? So the net direction is to the right, so which means that Kc value is always going to be greater than 1. Next, let's take a look at the second reaction. You have H2O plus HS minus. So let's write down H2O plus HS minus. This results to H2S plus OH minus. So we have OH minus plus H2S. So first we have to determine the acid-base pairs. So notice that this is a H2O plus H2O and OH minus. there is a proton loss, which means that this is the proton donor. So this is acid 1. So which means that this is base 2. Next, HS minus and H2S, accepting the proton, so which means that this is base 1 and this is acid 2. So we have determined the acid base pairs. The next thing we have to do is compare the two acids and compare the two bases. So we are comparing H2O with H2S. So let's take a look at the table. So we have H2O and H2S. So we have H2O right here and H2S right here. So because it's increasing acid strength, H2S is stronger than H2O. So H2S is stronger. And H2O is weaker. Now we have to compare the two bases, HS minus and OH minus. So you have HS minus, which is right here, and OH minus, which is right here. Notice that it's the stronger side, so which means in the reverse order here. So OH minus is stronger than HS minus. So OH minus is stronger than HS minus, so which means that this is stronger and this is weaker. So it always favors the weaker side. So which means that here the reaction goes to the left. So if because it's to the left, Kc is less than 1, and the reaction, the net reaction favors the formation of reactants. So the net reaction here favors the formation of reactants. So this is the idea behind the acid-base definitions of Bronsted-Lowry definitions, and using that definitions and determining the behavior of the acids.